Thank you very much. First of all the compliments to the organizers to organize finally this our meeting. Happy to be here. In my lecture, I will talk on a conflict between insects and some history on insect communication on the plant. And of course, thank you, Meta, to invite me here to give a talk. Okay. Stinkbugs are a very small group. Pentatominae are a very small group of insects which live all around the world. They are spread worldwide, and many species of them are important pests. It is especially a problem in Brazil because in huge fields of soybean and other plants, they develop and they live and make economically important damage. That's why maybe this is the reason that a lot of useful data on species biology, ecology, feeding habits and behavior just originate from the work of researchers in Brazil, in Embrapa, or at different universities. One of them is Antonio Ricardo Panizzi, a very famous researcher who published a lot of works on plants, and he found that subfamily Pentatominae consists entirely, they are of plant feeders, and important is that for them is characteristic polyphagy. For example, Nazara viridula leaves was recorded on 70 different plants in the neotropics, of which just 29 were reported as host plants. What is the difference? A host plant is defined as a plant that the bug feeds on and allows reproduction. It has the complete development of nymphs that will yield adults to be able to continue breeding to produce future generations. And of course, they are not always present in time or space, and that's why stinkbugs move to associated plants where they may feed, use shelter, lay egg on, but the nymphs are unable to develop and complete the life cycle. Insect communication runs through different media, through different channels, through air with chemical, visual, and sound signals. But when they land on a substrate, especially on a plant, they communicate with the substrate-borne component of their vibratory signals. Stinkbugs communicate with all these modalities. Especially important is communication with chemical signals, which runs communication in the field between plants that are not in contact, so at long distance. And when mates meet on the same plant, chemical volatiles trigger vibratory signaling that altogether brings them in close vicinity, and there other modalities come in play, like non-volatile compounds from plants and insects, vibratory signals, most probably also visual signals. There are differences between species and tribes in Pentatominae, but as an example or as a model type of sexual behavior, let us see the one of Nazara viridula. The male attracts females with the sex pheromone that brings females on a plant occupied by a male. And there, the male pheromone triggers female to stay stationary on one place and starts calling by vibratory signals the male. And these calling signals trigger males to move against the female. They also enable location of the female on the plant, and eventually there comes to copulation. On the other hand, male vibratory signals modulate emission of the female calling songs, and female calling songs modulate the amount of male sex pheromone emission. So a very, very nice picture. Now, just a few words on chemical signals. We were lucky to cooperate with Michel Renou, Jocelyn Miller, Miguel Borges, and Maria Carolina Blasioli Moraes from Brazil, so that we could get a lot of information on chemical signaling that explained us how vibratory signals play their role together with them. So chemical signaling evolved as early life forms and developed and is widely performed by molecules, tissues, organs, bacteria, protozoa, insects, large animals, and plants. So they are an ancient type of signaling. And most of the molecules of 6 and 6 aggregation pheromones produced by stinkbugs are species-specific and highly volatile and chemically unstable. And this instability and high volatility of these pheromones suggest that chemical communication occurs at specific distances and just for a limited time, a strategy to avoid chemical espionage by natural enemies and host plants. For example, the species within genera Hinavia and Nazara produce the same compounds as 6 pheromones, trans and cis isomer, and the species specificity and recognition are guaranteed by the different ratios between the two isomers cis and trans bisobolene. Here is a picture that shows you in few species the structure of male pheromones and various vibratory signals, of which we shall talk a little bit later. But nothing is perfect, and species specificity in pheromones is not perfect, and cross-attraction has been described in several species. For example, Nazara antenata responds to sex pheromone of Nazara viridula, and Nazara viridula is attracted by the sex pheromone of Tianta perditor. For example, Haliomorpha and Hinavia are attracted to the sex pheromone Plantia stali, and there are some more examples. Some pentatomid pheromones have chemical structures similar to plant compounds and compounds produced by plants. And for example, males of Piezodorus gildini produce the 6 pheromones of compounds also produced by rice, ginger, sorghum, wheat, and other plants. So this interplay of chemical signals and plants is a huge field of research, very important. And we can learn a lot of their data. But now we go back to our field on the plant. The plant insects have not much choice what to choose, which modality. They are small and they cannot emit low-frequency airborne sound. They can emit it, but the intensity is very low. They can emit only high-frequency signals, but dense vegetation strongly attenuates high-frequency sound. Insects can efficiently communicate with high-frequency airborne signals in the air, but there they are exposed to predators. So most of insects, when on a substrate, communicate with a substrate-borne component of their vibratory signals. But plant has tricks. Many years ago, Axel Mikkelsen and his co-authors, they gave the basis to understand how these signals are traveling through the plant, and it still stands. This is the fundament of understanding. So the insects communicate with bending waves. Plant transmit vibratory signals with low attenuation, and plants act as low-pass filter, highly attenuating signals of frequencies above 400 hertz. And finally, reflections at the phase border, that is between air and leaf, create echoes that follow the signal and significantly change the temporal parameters of transmitted signals. Now, a few examples. If you vibrate the plant with an FM signal in the spectral range between 50 and 150 hertz, you can see that spectra at 20 centimeter distance on cypress is completely different. Of course, also the temporal pattern of the signal is different. On bean, at a comparable distance, we can see the same phenomenon, a sharp peak around 80 hertz and the second peak, but again, a signal of different pattern. When they are transmitted through stem or rod-like structures in a plant, the amplitude does not decrease linearly, but with readily repeated peaks of amplitude maxima and amplitude minima at nodes and antinodes. And this has to deal with resonant plant, as our colleague Järne and his co-workers nicely described in their work. Frequency-dependent attenuation in different plants. Plants differ how they attenuate signals, and there are the so-called broad plants like ivy, soybean, and pea, where you see that attenuation starts sharply above 300-400 hertz. But we have also low-pass plants like bean, potato, and elder, where attenuation is very strong, around 100 hertz. So 100 hertz seems to be a magic frequency for transmission of vibratory signals through the plant with low attenuation, if at all. And of course, Stinkbugs arranged their frequency of their signals to the best frequency range. So in 35 investigated species, the dominant frequency of their signals lies always around 100 hertz, so from 70 up to 120, not higher. Now we come to the noise. Jürgen Tautz on the right and Jérôme Cassard from France. They published a lot of years ago, a nice work where they analyzed what abiotic noise is created in, well, not in nature, but in lab. And they state that wind and raindrops represent the main source of abiotic noise. And they have characterized wind-induced vibrations of leaf. They found that the basic frequency lies below 100 hertz, And basic oscillation of leaves induced by wind are independent of wind speed and velocity of leaf vibration range, between 30 and 60 millimeter per second in low and between 70 and 130 millimeters at high speed wind. Raindrops falling on the leaf induce bumps, a signal which is composed of two components, composed of the irregular phase at the beginning with high amplitude and high frequency up to 25 kilohertz, and the regular phase, that is the tail, with the amplitude decreasing exponentially with a half-life of 162 milliseconds. About the biotic noise, you have heard and you will hear new results of Rocksturm. I'm looking forward. Stinkbugs sensory and neuronal systems are adapted for vibrational communication through a narrow frequency window with low sensitivity to vibrations of frequencies outside this range, which means that outside this range, they filter out noise. But this advantage is on the same side disadvantage, because everything that happens in this narrow frequency range significantly changes temporal, frequency pattern, and pattern parameters. First, it has been shown with pure tones, not much an effect between around the 115 hertz, 2 millimeter per second velocity, not much with males, but females either stopped calling or decreased the repetition rate of their emissions, changed calling to rival song, and changed the signal fundamental frequency to increase the difference to the frequency of pure tone background vibration. Raoul Laumann, he made semi-field experiments with 75 to 200 hertz pure tones, and he introduced it on plants and looked in Eucistus hearers. What is an effect? And he found that searching behavior and consequently decreased number of copulating pairs and 24 hours of pure tone vibration of plants, it reduced the mating frequency of stinkbugs by 25%. So quite an effect, long term. But there is an exception, like always in biology. Spezia and co-authors, they have demonstrated that in the presence of acoustic Gaussian noise, Nesara viridula males moved to the source of subthreshold played back female calling song signals, which means that Gaussian noise helps or increased the intensity of the female calling song signals above the threshold level. Unfortunately, this research did not go further on. But the main problem is masking of signals. Normally or usually, stinkbugs communicate in a sort of alternation, so that signal is emitted in the pause between two consecutive signals, so that there comes not to overlapping or to masking of signals. And what is the effect in Eucistus hearers? The male reply song masks the female calling song, and in masked areas you get interference, which completely changes the pattern of the signal. If you look down, you see what is interference. Interference is a sequence of regularly repeated pulses that duration depends on the distance or the difference between masked frequencies. Now, here are some examples. Female song below, and male response above, and when they mask, in masked region, you get nice visible interference. And what the female does, the female simply prolongs the signal just to skip out or avoid masking. And what does the male? The male produces signals with frequency modulation that increases the difference frequency and decreases the effect of interference. We can mimic it also with pure tones, and we got the same result. Here again, you can see some reactions of females' prolonged signals. In B, with 100 Hz signals, you can prolong them also artificially. And below, in D, you see a huge difference between frequencies created by males that produce frequency modulated signals to avoid masking. Now, very shortly, how signals are produced. In Stinkbugs, they are produced by vertical vibration of abdomen. That creates species-specific signals which have been analyzed and described in more than 35 Stinkbug species, differing mainly in temporal pattern. This is an example of Nasara viridula. But on the other hand, frequency spectral characteristics are all more or less the same. The basic frequency lies around 100 Hz. But that is not all. They produce also species non-specific signals by tremulation, by percussion, and by buzzing. Buzzing means vigorous vibration of lifted wings. Tremulatory signals have been analyzed usually by aggression or when males tried to copulate with a female and the female rejected them. And these signals have very strong high amplitude. On the upper figure you see signals produced by abdomen vibration and followed by a sequence of tremulatory signals, and these tremulatory signals are transmitted over the air from one plant to another, that when both plants are not in contact, mechanical contact. Even more striking or interesting are buzzing signals. Buzzing signals that their duration lies from half a second to the longest one was 45 seconds of buzzing. And if you look down at spectra, at sine waves, you see this is almost pure tone. Almost pure tone. So with basic frequency around 100 Hz, and there you get a lot of higher harmonics extending spectra up to 2 kilohertz. So this is a very, very strong signal with high amplitude, and our recent results have shown that these signals are usually emitted prior to emission in the very early phase of calling behavior, prior to emission of the abdomen vibration produced signals. Here are spectra. You see very, very sharp peaks and no difference at all, or practically no difference between species. Now, vibratory receptors, a long story, but just an overview. The most sensitive receptors are located in the legs, with the subgenual organ composed only of 2 sensory cells, and in every joint we have recognized, found joint chordotonal organs, and when recording from the receptor nerves, we have found that high frequency cells, one sensitive to 200 hertz and the other sensitive to higher frequencies, come from the subgenual organ, and all the other, together with campaniform sensillas, they are sensitive in the low frequency range below 100 hertz. They all finally terminate in separate neuropiles, which have been called by Nishino in her brilliant work as medial ventral association center, and a little bit more words about it later. Now, these are the threshold curves. You can see low frequency receptor neurons responding in the low frequency range in a phase-locked manner, and then 2 cells, middle frequency and high frequency receptor cell, responding in higher frequency range. But there is another vibratory receptor organ located in antennae. There is the Johnston organ with 45 sculopedia, and the central chordotonal organ with 7 sculopedia, and they are very sensitive to threshold curve lies between 40 and 60 hertz, and with sensitivity around 1 millimeter per second. And when you observe mating behavior at close distance in the courtship phase, you can see that bugs antennate each other, which produces high amplitude, low frequency signals, which can be detected by antennal organs. Well, so Nishino and co-workers described the medial ventral association center as extensive mechanery sensory neuropile located bilaterally in all thoracic neuromeres, and axons from leg, body, and antennal chordotonal organs finally terminate and partly overlap. The projections into the MVAC neuropile suggest co-processing of complex vibratory information in addition to the sensory input from the abdominal, timbal, and leg chordotonal organs, and she and co-workers nicely described the anatomy and central projections of body chordotonal organs, timbal chordotonal organs, and pleural chordotonal organs. Just a few words on vibratory neurons. There are 3 types. The ascending neurons, getting information in the central ganglion and transporting it to the brain. Local interneurons and descending neurons. And about 15 different types have been identified. And in the future, we need to go into the brain to make a chain of events over the brain to effectors, as it is described for chemical signals. Now, at the end of my talk, we come to stinkbug conflicts. Mating behavior and communication has been described in more than 35 Pentatominae species by Pentatominae species by analysis of interactions between a single male and a male on different substrate. But conflicts between mates take place when more males court less females, when more females call less males, and heterospecific females or males are calling a male or a female of one or of the other species. Male rival song has been described several times, but only recently were described very complex female rivalry song, revealing their high diversity in species. And finally, interspecific communication in conflict situation is currently under investigation. Here we can see very similar signals of Hinavium picticornis female song 1 and female song 2 below, and comparable signals in Hinavia ubica. Not much difference when compared with signals of Eushistus heros below. And how it looks, female rivalry in Hinavia impicticornis. Female 1A emits calling song signals of the first type, and the second female in B suddenly starts to break the pulse train into a sequence of readily repeated pulses which silence female 1, but the female 1 then slowly changes to emit female calling song 2 signals with which they inhibit calling or signaling of the rival signal. Very different is in Hinavia ubica. They produce female rival song signals of very complex pattern. You see them in D and in E. And very similar female rivalry signals of complex structure with high amplitude modulation have been described in Eushistus heros. Now we shall finish with Nezara. Nezara emits female calling songs, and when two females are competing, they alternate with the female calling song signals A. But the rival female then changes the signal into a female rival song A, and afterwards to female song, rival song B type, and alternation with the female song shows steady duration and repetition time of one female, and the other female, yellow, it changes the duration and repetition time just to spoil emission of the rival female. But all of them both sing at spectrally similar or at the same frequency level. The same effect is we can observe in alternation with female rival song A type, but when they alternate with the second type of female rival song signals, they produce signals of similar duration, of similar repetition rate, but they change the frequency. So that the frequency difference between competing females is about 40 hertz. So the male can choose the female by the frequency. How and why, whether it does, we don't know. We haven't done these experiments yet. The male responds to all of these signal forms. Now, interspecific communication is a question, and you know the story on Nezara antennata and Nezara viridula. They produce very different signals, vibratory signals, but they have described interspecific copulation. On the other hand, sympatric Hinavia impicticornis and ubica have similar patterns of reproductive behavior, but they never copulated. They stop singing at the early stage of mating behavior. And playback experiments have shown that Hinavia impicticornis males respond to conspecific and to Hinavia ubica female calling song signals, and the same is true for Hinavia ubica. Now, this opened several questions and current investigations. We have investigated lately interspecific communication contact between Impicticornis and Ubica female couple when on the plant, together with Hinavia ubica or Hinavia impicticornis. And we have a lot of questions. For example, do females of one or other species recognize and call the alien species male? Yes. Do females of different species enter interspecific rivalry? Yes. What is male reaction? Do males recognize and respond only to conspecific calling song signals in natural conditions? No. Does Hinavia impicticornis or Hinavia ubica female react in the same way when on a plant with a heterous couple? That song repertoire differs significantly. No. These are preliminary results. We are going on in this direction, and I'm looking forward for the next meeting to bring you real results. Now, at the very end, I would like to thank to my friends and colleagues in Ljubljana and in Brazil. I miss you a lot. And of course, thank you for your attention.